I'll start recording now. So for all those at home and watching this later, all you missed is Alfred Wegener. He's a German scientist. Look at the slideshow and read it, because we're going to come back to him. So you didn't really miss much. Pangea, one landmass. Panthalassa, one ocean. Okay, so back to the interior of the Earth. So the crust is not the interior. It's actually the outer layer, but you can dig a hole, which then makes it interior. So we have to break it down into two different crusts, two different mantles, and two different cores, because we have to be able to explain why the Earth is moving, why the continents are moving, that sort of thing. So when we talk about the crust, we have two different types of crust. If you take away all the water, it's just one, but that's not the case. We have water. And the water is going to play a very important role on our crust, because the land, there's nothing above it. So if you went to the bottom, if you swam to the bottom of the ocean, one, you couldn't do it because you would be what? You'd be crushed. If you went to the bottom of a swimming pool, you notice your eardrums would like your ears hurt. You actually have to decompress them. If you blow out your nose, it lets the pressure equalize. Well, even 10 feet, 5 feet of water, there is some weight. So imagine 6 miles of water. What? 6 miles. Imagine all that weight. That's going to take that crust and it's going to smash it. And that is why the crust is so dense. It's dense because of the weight. So oceanic crust is crust under the ocean. It's denser because of the weight of the water. Okay. So that is why. And that's important. So important. And the fact that it's younger, we're going to come back to that because it's going to lead us right back to denser. So that is really, really important for us to understand and to know about, because whenever we talk tomorrow about what these plates are doing, we're going to come back to why it's denser, and then that's going to explain why it's younger. So this is kind of cool. It all comes back together, and really one of those chapters where you just learn so much. I mean, you can actually apply it. You can actually understand it. So there's math questions that I used to do, and I would get the answer, and I would be happy, but I had no idea why, and it was a crapshoot. Out of 10, I might have gotten 6 right. Okay, I took Algebra 1 3 times. So out of 10, I might have got 4 right. But the ones that I got right, I had no idea why I got them right. And yes, I took it. I think I only took it twice. But I failed it the first time. So continental crust is the opposite. So there is no weight on it, so it's light. It's thicker. It is thicker. Because nothing is smashing it down. And therefore, it's thicker, it is less dense and floats. So we're going to get back to that as well. So you have oceanic crust, which is anything that's under the ocean, and you have continental crust, which is the land. And it's older. You're not going to find, pretend I have my rock that's painted red. You're not going to be able to find this rock that's 400 million years old that has been continental crust the whole time. Yes, that rock that I showed you last week was found on the land, but it was originally continental. It was oceanic. I mean, I'm sorry, let me take it back. You can't find oceanic crust that old. That's just crazy old. And the only reason we found that one is because it was put on land. I got all backwards there. Okay. So that is the crust. Next layer down, oh, there it is. Hey, good job. Next layer down is not a layer at all. It is the moho. So Sequoia, if you're writing this down, you don't have to write that whole word down. This is just a boundary. This separates the crust and the mantle. It's invisible. You can't see it. It's not a layer. It's just this thing that we know is there, because when we study earthquakes, we're going to know that something happens to these waves whenever they go through the earth. And again, we're building this foundation, so we're just kind of learning about it today, but we'll talk about it in a couple weeks or next week when we talk about earthquakes. So, moho. Oh, I'm sorry, boring myself. That's bad. Mohorovic discontinuity. So if someone's making you mad, just say, don't be a Mohorovic. And they won't know what you're talking about. Okay, so moho. I think if you're doing slides, I think I only had like one blocked out, 1 or 2 words, pretty small. Okay, now we get into the mantle. So it's not just a mantle. Matter of fact, today we're probably going to only talk about the 2 different types. We're not going to call them mantle anymore. We're going to separate them. We're going to separate them into 2. So when you look at this diagram here, you see the crust and the lithosphere. So the very, very top of the crust or lithosphere is actually the crust. They're almost together. And that is important. And then the asthenosphere is below it. So the lithosphere is the upper mantle. It's cool. It's rigid. If you don't know what rigid means, it's like brittle or hard. Because when we talk about the mantle is it's almost soft. It's like a plastic that's heated. So it's or Play-Doh. It's very much like Play-Doh or do you ever mix starch, the mystery goo with starch and water? It's kind of like that. Yeah, Jell-O. It's got that Jell-O-y type of feel to it. So the asthenosphere, and these are a little bit wordy. This is the lower. This is hot, but what's very, very important is that it is solid. It's not hot enough to melt it into a liquid, but it is solid, but it has the ability to flow. So that's really, really important that we understand this. If I take Jell-O and I put Jell-O in a bowl, it's so annoying. Let me go to my annotation. If I put Jell-O in a bowl and I take that bowl and I flip it upside down, then I'm going to have a Jell-O mound that looks just like the bowl. It's gonna hold its shape. So it's a solid, but I can wiggle that Jell-O and it'll move. Therefore, it has the ability to flow. So if I put it on top of a table and I tilted the table, it would probably roll. If I left it and I tilted on top of the table, it would probably just slowly move down. So it has an ability to flow. That's really, really important because it is a solid. If I take Play-Doh, I had a piece of Play-Doh. Where is it? Where's my Play-Doh? Oh, here it is. I can't change this because this was my daughter made this. She made this little dude. But I can take, this is Play-Doh. So you know what would happen if I took this and smashed this. You know it. I just don't want to do it, She just made it. I drop it. But it's still soft and it would smash into a ball. But it's been sitting on my desk for about 5 weeks. So it is solid. It is not flowing, but I can manipulate it. I can squeeze it. I push it down. I can probably roll my hand on it. Therefore, it will act like it is flowing. I hope that makes sense. Sometimes I go the long way around to try to explain something because I don't see your faces. And even if you were unmuted or unmiked or unvideoed and I can see them, I don't because I only see the slideshow. So I do explain things a little bit extra, and I apologize for that. So Play-Doh and Jell-O are our examples for this asthenosphere. And this is going to be really, really important because it's going to explain why we're moving. Okay, so before we get into that, the last layer is the core. So we know that the core is hot, but we're going to break it into two different cores. And that is really also very, very important, because the outer core is actually the only liquid layer of the Earth. The outer core is the only liquid. So the asthenosphere is a solid that flows. It's hot, but it is not a liquid. The outer core is the only liquid. I used to, and I consider myself very, very fortunate. Outside, in, I think it was 2003, I got a new job outside of Pittsburgh. It was a big environmental lab, and we tested water, and we tested soil, and we tested air, we tested everything. But one of my jobs was I got to go to Pittsburgh steel mills, and I got to walk around these steel mills and sample water. Now, it's not significant to you, or at least might not be, but my people, my grandparents, my uncles, my dad, my great-grandparents, everybody worked in the steel mill. Everybody worked in the steel mill. And then they shut down in the mid-'80s, late 80s, and that whole world was stopped. There was very, very few that still ran. So Pittsburgh was basically just a steel mill. But when I talk about walk through steel mill, I'm talking about these were 1 mile to 2 miles long. One steel mill, miles long. It was like a city. They had trains and stop signs and trolleys and almost like taxis that took you from one part of the plant to the next. I mean, we're talking a city. So I was very fortunate. I got to walk around where my people walked around, my grandparents, where they worked. It was just neat. But one thing that I did is I had to go near these vats of steel. And if I got within a football field of them, I could feel the heat, just crazy, crazy hot. And that's exactly what the outer core is. I mean, that's it. It's molten steel, metal, iron, liquid, nickel, all that. So very, very, very hot. The inner core is the opposite of liquid. It is solid, but it is the hottest layer. That's weird, right? But it is solid because it's under so much pressure. So if I took something and I added pressure to it, I'm going to heat it up. I'm going to heat it up till eventually melts. That's why this is liquid. But if I add even more pressure, imagine how much pressure is on the inside of the Earth. It's a crazy amount of pressure. It's where everything happens. It's the core. But it is so much pressure that it doesn't melt. And it can't. If it melted, then we would have our Earth would be jello. It'd be like someone, I don't know, I'll just say it. Someone like threw up in space. It would just kind of go, in one general area. And it would not be a world. It would be, terrible. Even Jupiter has a solid layers, a solid core. It has to in order to have its shape. So outer core is liquid, inner core is solid. So one thing, and we will do this as a warm-up. You have your 6 layers. So for some reason, these 6 layers are the hardest thing in the world for my students to remember. When I used to give you paper tests and you would come in on a Friday and take the test, I would tell you that 12 points were going to be you naming the layer and defining it. And for some reason, it just never sinks in. So the first thing you have to do is you have to remember that you have the crust, you have the mantle, and you have the core. And then we break that into 2. So you have the inner and the outer. You have 2. You have the lith and you have the as then. And then you have 2. You have the, again, I'm sorry. Wow. You let me. It's not the inner and outer crust. You have the ocean. And you have the continental. This is inner, or out. Let's go outer. Wow. and 2 words. You just want to remember 2 words for each. So as you go back through, and I'll show you what you should do when you go back through. So the ocean is young and dense. Continental is old and light. Lithosphere is cool and hard or rigid. Asthenosphere is solid that flows. Outer core is only liquid. And the inner core is the hottest solid. We'll have a Venn diagram or something that goes, or something that you can drag, but that's it. If you can remember those 2 words for each one of those, you're in great shape, and that'll help you throughout this course. And then one of those things that you will come back to if you take environmental science or ecology, this is something that you will learn about again, so it'll help you out to remember it. So those are the 6 layers and the 2-word definitions with each. So if you went back, if I could go back. So outer core, you could just like underline only liquid. Inner core, hottest and solid. Cool, you can see what I'm doing here. You can go back and underline, or if you're a highlighter, if you were handwriting these, you could go back and highlight, and that would just help you out. That would just keep everything locked into your brain. Okay, so the next thing, or the last thing that we're going to do today is you have a slide. For some reason, again, I don't have it, but you have a slide on your slideshow that is the same as my exit ticket. So if you go to your Google Classroom and you click exit ticket, it's gonna look like this. I have a little note: if you're in class but you do not do this, you can't turn it in late. This is participation, so it's 15 points. My gosh, I'm just throwing points at you. But if you don't do it and you don't turn it in by 11, you don't have to do it, but you can't get rid of that 0. So all you're doing is you're clicking on it. A copy's already been made for you. Don't worry about the 2 types of crust, but you have lithosphere, inner core, outer core, crust, and asthenosphere. You want to grab these and drag these. So click on them. If you think this outer layer is the outer core, bring that to it. As soon as you are done, you can submit it and it will be turned in. Everybody know how to find that? Everybody good with that? Okay, awesome. Anybody have any questions about that? Nope. Okay, awesome. If you have any questions, you can stick around. If you want to do this while I'm here, you can stick around and do it, and I will help you if you need it. If not, you can go ahead and sign off, and I will see you all tomorrow.